Alright, welcome back to Particle Physics and the Standard Model. This is lecture 46, and in the last class we saw the solar neutrino problem in more detail, and in particular we determined the baseline for these oscillations to be in natural units 5 times 10 power 17 inverse electron volts, and the energy of the neutrinos by just considering the Q value of this nuclear reaction to be about an MeV. And with that we try to ballpark what the delta m square that could be measured here is, and found that it was 10 power minus 12 electron volt squared, which is completely wrong compared to what is being measured. Okay, the measurement gives us the value at around 10 power minus 4 electron volt squared, and the mistake we made was that we had assumed oscillations in vacuum. In fact, we had assumed propagation of the neutrinos in vacuum. Okay, that is something that we had needed to change, because there is always going to be dispersive effects when you have propagation of any species in a medium. We are already familiar with that in optics, right? Photons traveling through glass or water undergo dispersion, correct? And the effective Hamiltonian that you need to write down then for the equation of motion would essentially be modified. That is what is going on here as well. The sun should now be thought of as a ball of electrons, a medium of electrons through which neutrinos are propagating. So, in the non-relativistic limit I can modify the Hamiltonian, which I can do by first inspecting the Lagrangian and seeing that the interactions of neutrinos with the electrons can now be re-expressed in terms of the number density of the electrons, and there is a crucial factor of GF, the Fermi constant in front, which is what we call the matter potential, and which I argued is actually a Fermi pseudo potential. Okay. All of this just comes from the forward scattering of neutrinos, neutrino plane waves in the presence of matter. Okay. So, we ended by saying that this should of course modify the probability for flavor conversion, because that is the modification term that you need to put in, acts only on the electron neutrino eigenstate. Okay. That would indeed solve the solar neutrino problem and also give you the correct value of the delta m square that you get from solar neutrino baselines. Alright. Now, having said that, we still do not know really how to order the 3 eigenstates of the mass eigenstates in terms of the flavor eigenstates, and the ambiguity comes because what is actually observable is the sine square of this combination of delta m square L and all that. Okay. And that automatically means that there is a delta m square going to minus delta m square symmetry in the problem. Put differently, you do not know whether you are measuring say m2 square minus m1 square or m1 square minus m2 square, right. So, how do we resolve all these ambiguities? Okay. You will find that, okay, since there are only 2 delta m squareds measured, okay, you can use the following convention. Okay, and be consistent about how you separate the scenarios. What is that? We fix always, you say that m2 square is always larger than m1 square. Okay, what does that mean? It means that delta m12 squared is nothing but just in the absolute value is nothing but delta m12 squared, which is as we defined before m2 squared minus m1 squared. Okay. So, you do that first, then you say that what you call delta m12 squared, right, is smaller than the other one that you measure, which you call delta m13 squared. Okay. Now the sign of this is not yet determined. Okay. So I am going to put this under an absolute value. Alright. Said differently, I am going to identify, I am sorry, I think I wrote this the other way around. I am going to identify the solar neutrino difference in the mass squares to be m1 delta m12 squared, okay, and I am going to identify the other one, the atmospheric neutrino delta m squared, as delta m13 squared, okay, because I only have to, these are just two measurements, I do not know yet which one is what, I am just going to make this identification, okay. And indeed this is 10 power minus 4 roughly, and this is 10 power minus 3, right. So this is fine, okay. So now how many free parameters do I have? How many observables do I have actually at this point? So I have 3, right. How did I get 3? 3 observables. What are they? Delta m12 squared, delta m13 squared, but I did not fix the sign of this, correct. So that is yet another sign of delta m13 squared, okay. So this is 2 cases. So this is fixed, but this obviously corresponds to 2 cases, there is a plus and a minus, correct. So that is why we can order the neutrino masses in 2 different ways, okay. And I am going to show you, I am going to draw a picture to depict how we do this, okay, the 2 cases. The first case is, I am going to draw a spectrum and I am going to draw it in a slightly interesting way. This is the way you will see it in textbooks, okay. So these basically are, these correspond to the 3 different masses of neutrinos, okay. And in this case I am going to call this m1 squared, okay, I am going to call this m2 squared, m3 squared. So 1, 2, 3 just comes in the correct order, the order that you expect, and for that reason this is called normal ordering, okay. So alright, so you see all I have done is I have this measurement, right. So I still have this is nothing but delta m solar mass squared, and clearly that is smaller than, the way I have drawn it, it is smaller than this, right, which is delta m atmospheric squared. You might wonder, isn't that delta m13 squared, why am I drawing this arrow between 2 and 3? It does not matter actually, okay, you can call it between 1 and 3 or 2 and 3, that does not matter really. Why? Because the difference between 2 and 1 is so small compared to the difference between 1 and 3 that might as well just both of them are roughly equal anyway. m23 squared is roughly equal to, I will just write it down so that it is not, so there is no ambiguity, okay. So I have drawn many arrows here, but do not forget that this corresponds to delta atmospheric square and this corresponds to the solar neutrino measurement, okay. Now why did I draw these bands? That is because in the bands I wanted to depict how much of each of these, okay, eigenstates contain, these mass eigenstates, how much flavor eigenstate do these actually contain, okay. So let me slightly modify this. Once I do some shading, you will understand why I am doing this. Okay, so it is over here and this comes somewhere in the center and it is over here. Okay, so I am going to do some shading here. Pay attention carefully here. So this box I am going to shade green. Similarly, this box I am going to shade with green and this box I am going to shade with green. Okay, and the last box I am going to just shade with, let's call it orange. This is orange. And the central box I am going to leave it blank. So just call it white shading. Okay. So why am I doing it this way? These basically, what are these ultimately? These are the PMNS matrix elements, okay, but re-expressed in a certain way. This is tan square theta 1 2, okay. So this tells, remember the parameterization that we had in terms of rotation matrices and the CKM phase and in this case the PMNS phase with 3 rotation matrices. So that is the rotation angle that tells you how much mixing is going on between the first and the second eigenstates, mass eigenstates, right. And in terms of the PMNS matrix, this is also very easy to derive. This is the ratio, the square of U E2 divided by the square of U E1, that is tan square theta 1. Okay. Similarly, we have this for the mixing between 3 and 2, and finally UE3 is just like that, sin theta 1 3 e power I delta with a minus. Okay, so that if I take the modulus, I can get rid of the phase, right. So the 3 mixing angles are here, and what I have done here is I have shown how much mixing has happened such that what amount of flavor is available in each of the 3 mass eigenstates, okay. And in particular the green corresponds to how much electron neutrino is there, okay, and the blank one corresponds to how much muon neutrino is there, and finally the orange box, the orange part corresponds to how many tau 1 neutrino is there, how much tau 1 neutrino is there, okay. So for example, we know that M1 square is mostly electron neutrino and the other half is a rough admixture of tau 1 neutrino and muon neutrino, okay. But the same cannot be said for the other 2 eigenstates. In the second eigenstate M2, it is almost an equal admixture of all 3 flavors, right. And all one can say about M3 square is that the nu 3 has very little electron neutrino content, but has a large admixture of tau 1 neutrino and muon neutrino content, okay. So that is the meaning of this. To be a little more exact, I should have actually drawn an even smaller region. Actually I should have shaded a very small region, that is the region I should have shaded, okay. Okay. So so in this I have put basically 3 larger than 1, okay. I have basically taken the sign of this to be plus and that corresponds to the normal ordering. What happens if I take the minus case? That is the case that is known as inverse ordering or inverted hierarchy, okay. So, I am going to draw that picture now, equivalent to this. Now, look at the distance between m1 squared and m3 squared. I am going to draw something, a distance that is somewhat similar here. Okay. So, it is like this. Again, this picture is not to scale, these heights are not to scale. Okay. But anyway, I am trying to draw the separations to be roughly the same on both the left and the right. Okay. Now, in this inverted ordering, m3 squared is smaller than m1 squared, right. So, this is m3 squared, this is m1 squared, and this is all as usual m2 squared. Why? We always fix m2 squared to be larger than m1 squared, right, that is the fixing here. So, that goes above that, and just for completeness sake I am just going to say this corresponds to the delta m squared from solar neutrinos, whereas the entire thing corresponds to atmospheric neutrinos. Now, once again, to complete the picture, I am going to draw m3 squared contains very little electron neutrino content, and there is an almost equal admixture of tau-on and mu-on neutrino content, right. So, that is what I have drawn here, and m1 squared we just saw. I am just basically redrawing the whole thing here, but it is for the sake of completeness it is important. Okay. So, there we go, and finally m2 squared is an almost equal admixture, right. So, there we go. So, that remains, nothing has changed there. The amount of flavor in each of the mass eigenstates, that has not really changed. Okay, it is only the ordering of the masses that has changed. So, let us call this by its name, inverted hierarchy. So, people use hierarchy and ordering interchangeably here. Okay, good. So, did that give a good picture of how we order this stuff and how to think about flavor eigenstates versus mass eigenstates? Okay, get used to the notion of this. Okay, everything again, remember we talk about when we talk about particles we talk about quantum states, and once we talk about quantum states we can choose any basis we want. Everything depends on what is it that you are trying to measure here. Okay. Now, finally, where is 0 in all this? Could any of these masses be 0 here? Have we ever talked about 0 mass in this entire discussion? Not at all, right? All the measurements that we can make are in the differences in the squares of the masses. Okay, that's the only thing we can actually measure in all this, because that is the only quantity that gets into any observable that we can construct, namely probability of flavor conversions. Correct? So, this picture won't be complete if I also don't depict where 0 is, and I am going to put it this way. Okay, how far away this entire picture is from 0 is not known. That is why I am putting 2 question marks. Okay, or said in words, the lightest, let me not write it in green in case you think that corresponds to the nu E, I will just write it in blue. The lightest neutrino mass, right, or I do not need to write eigenstate anymore actually. The lightest neutrino mass, right, is consistent with 0. So, we actually could have in nature a massless fermion, absolutely possible. Okay, it is a very interesting and weird thing, but it is absolutely possible. From what we know in neutrino data, it is completely still possible. Okay. So, what else do we know about neutrino masses? We know the delta m squareds. There is one other thing we do know, okay, and this is another piece of good luck that we have in how these calculations come about, how the experiments are done. We do know bounds on the total mass of neutrinos. Okay. So, what do I mean? The masses of the 3 eigenstates, okay, if you add them up, this is a quantity that you can measure from in the beta decay spectrum. In particular, if you look at the end point of the spectrum, this is something that you can measure. So, what is beta decay? At the hadronic level at least it is this, right. So, by making careful measurements, you can actually try to determine what the total sum of the masses of the eigen masses of the neutrinos are, okay. But we have not actually measured it. What we do have instead is a bound, an upper bound, which is 0.8 electron volts, okay, and this bound comes from an experiment called the Catherine experiment. So, if you Google Catherine, you will see some very interesting pictures of the detector of this experiment being carried through some villages in Germany and all that, okay. They had a hard time putting it on a truck and taking it to the dedicated experimental site, but that was the experiment that set this bound. This may not be the most up to date value that I am quoting, but you know the order of magnitude stands, okay. Now, an even more stringent bound comes from, so might as well put an I here, comes from cosmology actually, okay, of 0.2 electron volts, 0.12 electron volts, okay. So, I am going to put a star here because this comes with some caveats. We are not going to get into that. There are some assumptions that need to go into it, depends on the observables that you use, but I am not going to say anything more about this, but from cosmology you get another bound like this, okay, and the curious can go check this up, look this up, okay. So, what does this mean for us? Notice that the neutrinos, right, the difference in the squares of the masses is around 10 power minus 3, 10 power minus 4, right. That means one could guess that the difference in the absolute value of the masses themselves, right. See, this is not delta m squared anymore, not, right. This is around the 10 power minus 2 electron volt scale, correct. So, literally the separations that I am drawing here, okay, here I have drawn M3 squared and all that. If I drew the actual spectrum with the 3 neutrinos, right, on an average I would expect 10 power minus 2 electron volts as the separation, yes, okay. Whereas the total mass is constrained to, right, the total mass is constrained to 10 power minus 1 electron volt roughly, yes. So, now the question is, where is this spectrum sitting? These 3 neutrino masses, if they are you know they are either close to 0. So, we do not know, see here we do not know how close they are to 0 here, right, that is why I put this double question mark here, right. So, either the entire spectrum, so let me write the possibilities, either the entire spectrum is close to 0, okay, which would mean they look, so let me write appear well separated on 10 power minus 2 electron volt scales. That is one possibility, completely possible. Why? The highest mass would be a few times 10 power minus 2 electron volts, right. That is still fine because we only have an upper bound of 0.1 electron volts. So, you are way below the upper bound and close to 0, okay. It is either that, okay. So, let me probably draw a picture to show you what I mean. So, I have a spectrum like this, let me redraw that spectrum. This case corresponds to 0.1 electron volts being here, and then the 3 neutrinos are, so okay, this is also not the best way to draw, but the 3 neutrinos, 3 eigenstates are basically like this, okay, and this is roughly where 0 is, okay. So, on 10 power minus 2 scales they appear well separated, right. If this is 10 power minus 2, I do this 10 times, I get 0.1 electron volts up here, yes. So, either that is one possibility or the other one is, let me draw a picture this time first. So, I have 0.1 electron volts here and the 3 neutrinos, okay, seem to be squished together like this, with again 10 power minus 2 eV separation, alright. So, in other words, 3 neutrinos appear near degenerate on 10 power minus 1 electron volt scales, okay. That is, the neutrinos are all roughly 10 they are all, their actual mass is actually 0.1 electron volts, okay. That is what I mean by this. They are all very close to 0.1, they only their separation is about 10 power minus 2 electron volts. So, they are finely separated on these scales. It is either that or the natural mass scale of the neutrinos is only 10 power minus 2 anyway, and on that scale they are well separated, okay, because this is just the upper bound. Okay, that is the idea. We do not know whether the neutrinos are 0.1 electron volt or 0.01 electron volt, and there is 2 different ways to visualize this, okay. So, in the next few minutes I am going to wrap up the lecture by talking about yet another independent way of measuring oscillations, okay. And these are experiments that can be done with reactor neutrinos. Why reactors? So, the sun produces neutrinos and then the earth's atmosphere you produce neutrinos through cosmic rays hitting the nuclei and forming a hadron shower. But you do make a lot of neutrinos in atomic reactors also, right. You after all use a lot of weak processes. We are doing fission, fission is manifestly a weak process and you will always get neutrinos out of this, right. So, reactors are very good copious sources of neutrinos, and you also have a handle on how many neutrinos you are producing here, right. So, you know the site of the reactor. So, if you want to measure neutrinos coming out of that site, you can also control where to put your detector. Yes. So, there are many reactors in the world that are also used for neutrino experiments, and what these can do is, remember we measured delta M12 squared and delta M13 squared. You can, this is with this is with solar baseline and this is with atmospheric or earth baseline, right. Now you have yet another handle. Now you have a third baseline, and you can basically do one more measurement and cross verify the measurements that you made using atmospheric and solar neutrinos. Okay. So, that is the basic idea, and in the next lecture we will see exactly how this idea is implemented in we will take one example, the CHU experiment in France, and see whether that is indeed consistent with the atmospheric and solar neutrino measurements of differences in neutrino mass square. Okay. So, we will do that in the next class. Thank you. See you then.